The next topic I want to discuss is selection of gears. And these topics, or this topic I'm going to discuss, comes from an example in the book, on two examples in the book, page 278 and also page 280, as well as an example on page 274. So the selection of gears is really how you look at a particular gear set with a particular diametral pitch. And so this varies and depends on the condition under which the gears are going to be operating, the types of materials that they're made of, lubrication, and a host of other factors include loading, how often they're going to be used. This is a fairly simplistic approach to gear selection. I'll talk briefly at the end of this of gear selection of and design formula that are available on manufacturers' websites such as Boston Gear. So here's the example. A gear set has to be selected. The input of the motor is 1 horsepower and it operates at 1200 RPM. The output speed is 600 RPMs, and so in this case we need the gearbox to reduce by a factor of 2. The center distance of the two gears, the two wheels in this case, should be 7.5 inches apart. And the goal of this is to specify both the gear set and the diametral pitch. In this example, I'm going to focus just on specifying the diametral pitch, not on the size of the gears or the number of teeth on the gears yet. So in order to specify the diametral pitch, what you would do is you would go to a gear manufacturer's website. That gear manufacturer is going to create a bunch of varieties of gears, and those gears are going to be based on different materials. They might be heat treated differently. They might have different tolerances. But what you would do is you would come to a catalog like this, or potentially equations by the manufacturer, and you would find 1 horsepower. In this case, it's the row of 1 horsepower, and we want to be able to transmit that 1 horsepower at 1200 RPM. So the cell that is at the intersection of 1 horsepower and 1200 RPM specifies a suitable diametral pitch, and in this case the diametral pitch is 16. Now make note of this in the book as well. This is for mild steel gears with a standard face and for 20 degrees. So as I said before, this may change depending if you're going to use a different type of gear or a non-standard type of gear or a higher tolerance gear. And the other thing to note on this is I can transmit 1 horsepower at 1200 RPM. I could also use a gear with a diametral pitch of 12 or 10 or 8 or 6 or 5, depending on the gear sizes that you want to you have access to. So that's how this table reads, and again this comes from the selection of the diametral pitch. At this point we haven't selected the size of the gears or the number of teeth on the gears yet. The next topic I want to talk about, and I'm just going to start on this and then we'll go over these examples in class, are the types of gear trains. There's many different types of gear trains. There's many different applications for gear trains. They can be boiled down to about 4 basic sets of gears, gear trains. So the first one is a simple gear train. And in a simple gear train, the meshing gears, there's only a single gear on each shaft. In a compound gear train, 2 gears are rotating at the same shaft. There might be multiple shafts. This will be easier to see a diagram of. We can talk about a worm gear set, and then planetary gear sets. So in this lecture, we will get to derive the kinematics and the mathematics behind each of these gear train types. It's important to note that the fundamental law of gearing still applies to each of these types, and each of these types has both their positives and their negatives. I'll particularly talk about one compound gear trains. These you will find in most manual transmissions of automobiles. Planetary gear sets you find in automatic transmissions. And a new or slightly new term that I want to reintroduce, or introduce a new term rather, is this idea of train ratio. And so train ratio is either the velocity ratio or the torque ratio. And train ratio and the range of train ratios depends on the type of gear train available. So simple gear trains, you'll see maybe around the tens in terms of gear reductions. Compound gear trains, you'll see maybe tens to hundreds. Worm gears, you'll typically see at a very high gear train reduction and are typical of 100 to 1 and higher. And planetary gear sets vary on these applications. I'm going to cover the ideas behind these gear trains now, and then we'll come back in class and go over the solutions to the problems. This is an example of a simple gear train. What you see here is that there's one gear per shaft. So the first gear, in this case denoted as gear 2, is meshing with gear 3. And this gear 3 is meshing with gear 4. The P sub D of each of these gears need to be the same. So in this case, the PD of gear 2 has got to be the same as the PD of gear 3, has got to be the same as the PD of gear 4. And here is the relationship. So in this case, the velocity ratio. The velocity ratio between gear 2 and gear 3 is N2 to N3. In this case, negative, because if gear 2 spins clockwise, gear 3 will spin counterclockwise. The velocity ratio of gear 3 to gear 4 is negative N3 to N4. And if we look at the overall velocity ratio of 2 to 4, it's a positive N2 to N4. I'm going to unpack that and discuss that, but you should think about this in the context of this simple gear train. And a good rule of thumb here is that the ratio between two gears should not exceed 10. And this is done from a sizing standpoint. I'm going to skip over this example right now and come back to it. This is an example of a compound gear train, and I know it's maybe a little hard to see, but what you've got here is gear 2, represented here from a vertical view, is meshing with gear 3 on this shaft, and gear 3 and gear 4 are fixed to this shaft, so they rotate at the same RPM. Gear 4 is meshing in this case with gear 5, and gear 5 is on the same shaft and rotating at the same RPM as gear 6. And finally, gear 6 is meshing with gear 7. This is what is referred to as a compound gear train. What's interesting about this is gear 2 and gear 3 have to have the same diametral pitch. Gear 4 and gear 5 have to have the same diametral pitch. And gear 6 and gear 7 have to have the same diametral pitch. But they don't need to be the same across non-meshing pairs. What I've described over here is the velocity ratio for meshing pairs. However, we run into a slight complication because gear 2 and gear 7 don't directly mesh. So we're going to go ahead and derive the velocity ratio for those gears as well. Again, I'm going to skip over this example and we'll come back to it. The previous example was a compound non-reverted gear train. This is an example of a compounded and reverted gear train. And what you'll see here is it's a compound gear train. In this case, we've got the input shaft connected to N2. We've got these two gears mounted to this shaft. So gear 3 and gear 4 spinning at the same omega. And finally, gear 4 is meshed with gear 5. The kinematics are the same behind this as the previous compound gear train. The one added complexity of this is that the input shaft is in line with the output shaft. So this is a much more compact representation. And this is actually the type of gear train that are used in manual transmissions in cars. Skip over this example and move on to the next. An example of a worm gear train. In this case, we've got the worm and the gear, and the velocity ratio for this worm gear train is the number of teeth on the gear to the number of teeth on the worm. In most instances, though not all, the number of teeth on the worm is 1. And this is just a small animation of this worm gear spinning and driving the other gear to rotate. We'll come through that. And finally, the planetary gear set. These actually are the types of gears that you find within drills. If you've ever operated a KitchenAid kitchen mixer, these are the type of gears within that. It is a slight optical illusion, but let me try to unpack what's going on with this planetary gear set. The input shaft is connected to this sun gear, in this case gear 1. The input shaft and this carrier are not connected. So the omega of the input shaft does not necessarily equal the omega of the carrier. This carrier is pinned to these planets, and this planet is meshing with the sun gear. And finally, these planets are interacting with this ring gear, and this output shaft is connected to the ring gear. So this gear train has got 2 degrees of freedom, which means that we need to specify 2 inputs to the system. And in this case, these are 2 omegas of the system. A slightly different view of a similar system shows a little bit about the how one of these systems might be configured, but you've got the same type of configuration here. We won't go over the solution of this yet. We will unpack this example. Some things that we should be aware of when we're designing gear trains. The velocity ratio typically is limited to 10 to 1 or less. And as I've discussed in class, this is just from a size perspective, but it's also from a momentum perspective. So if you've got a small gear connected to a large gear, we end up with a whole lot of momentum. We typically assume power to be conserved within a gear train, though there are some losses due to friction. When we look at gear trains, we're typically focused on torque and angular velocity changes. I'll show you the mathematics behind this, but the idler pulleys or the idler gears that we talk about have no effect on the overall train ratio. They typically have effects on only the center distance, the spacing, and the direction. Spur gears typically 98 to 99% efficient. Helical gears are less efficient because of sliding friction. Parallel helical gears 96 to 98% efficient, and crossed helical gears, so when we're dealing with shafts that are perpendicular, are 50 to 90% efficient.